Hello everyone, this is lecture 5, model fitting. So the learning objectives for this lecture is to understand the differences between curve fitting and interpolation. So the solution is already available to you. I just want to walk you through the idea of this two type of curve of model fitting, right? So again, this is curve fitting or model fitting and interpolation. Okay, I'm gonna tell you the idea behind interpolations, curve fitting, and then toward the end of the lecture, there is some error type that occur in model fitting technique. All right, so let's talk about the relationship between model fitting and interpolations. Let's say that you have some data points in more particularly, you have the n data points of the form x sub I comma y sub I, right? So the first component is the x value, the second component is the y value. And you have some functions f of x describe the quantity of interest at all points, okay? Um, but most of the time you don't have the luxury to have a very specific function at the beginning, right, to deal with, right? They're not going to give you in real world problem, they're not going to give you like, oh, this is the linear functions or equation of a line, or this is the quadratic function or the polynomial functions of degree 2. Oh, this is not exponential function, this is not logarithmic functions, it's not sine or cosine. So you don't have that luxury at all, right? So most of the time you observe the world and you just collect a bunch of data, right? Now you have the data, but still you want to make predictions in the future or certain predictions within the data that you already collected. Let's say you collect the data 1, 2, 3, 4, 5, right? And then you build up the model and then you use either curve fitting or interpolations. And then it's allow you to make a prediction between for the point between 1 and 2 or the points between 2 and 3, so on and so forth. Okay, so that's the idea that occur in curve fitting and interpolations, right? So what are the differences between curve fitting and interpolation? So the idea for interpolation is that um, interpolations, you derive derive a curve or a function that goes through all the data points regardless of what function ends up look like. Okay, so let me scroll down a little bit and show you the graph, right? So let's say you have this collection of data, okay? And then this is the observations that you have, right? And then again, you want to make predictions in the future. And sometimes you want to make prediction with of the data point between this 2 point or between this 2 point or between this 2 point, so on and so forth. Okay, so interpolation is that this is the interpolating curve, right? So it's gonna fit all the points, right, in this curve, using this curve. Okay, so that's the idea of interpolation. Right, so the function goes through all the data point regardless of what function ends up to look like, right? As long as the curve you have, you go through all the data points. All right, so this interpolation typically used when there is a great confidence that there are no measurement errors, right? So when you collect data, when you make observations, when you make measurements, there's always human error involved or some measurement involved. So if you are actually confident with the measurement that you make or with the observations that you collect, then you can just use interpolations again, because the idea that for interpolation is that the function goes through all the data point and you are confident with the measurement or the observations of this data point. Okay, and the idea, again, the third idea of interpolation So the third idea of interpolation is that you don't have multiple values of y for a single x. So this is quite the same as the definitions of functions. Right? In pre-calculus or calculus, you define functions to be relationship between the independent variable and a dependent variable, or relationship between x and y. So one value of x corresponding to one value of y. Right, so that's the idea. Right, so if you have these three ideas together, then it's good that you use interpolations to fit a curve into the data points that you collect. Okay, so there are some drawback and also an advantage of using interpolations. So a drawback is that, of course, the real-world data almost always contains some sort of measurement errors. There's no way you can make the correct measurement all the time. Right? So that's the big drawback, right? You have to be aware that there's always contain measurement errors. And because the function that you produce that go through on the data point, right, can be very, very widely, even with the slightly change in the data point, right? So that's the, even though it looks very, very nice that your curve go through all the data points, but if you make a slight change in the data points, then your function will change sometime drastically. Okay, and the advantage of using interpolation is that it can make predictions about the y value within the range of the given data point. Okay, so I mentioned earlier that, okay, using interpolations right here, the curve go through on the data point, and you can make predictions between x1 and x2, make predictions for the y value between x2 and x3, so on and so forth. And at the beginning, we also talked that we don't care about the end behavior or the behavior of the function end ups look like, right? So if you can continue with this curve, it may go to infinity or negative infinity or positive infinity, right? So, but the advantage again is that it still give you a great confidence that you can make predictions for the y value within the data point that you collect. Okay, so that interpolations. Now, the next one is curve fitting, right? So it's another type of model fitting. So for the curve fitting, you seek some function that will be a best fit for all the data point. And this curve that you produce does not necessarily have to go through all the data point. Okay, and there are some criteria that you can use to make to produce a best model to fit all the data point. And we talk about that in lecture 6 and lecture 7, those criteria. And it is typically used when there are significant error bars in the data point. The error bar is that there are some differences between the point on the curve that you produce with the data point that you observe, right? So there is some distance within between the point on the curve and the point that you observe. Okay, and of course, the big advantage of the curve fitting is that curve fitting functions are less susceptible to drastic change when there are changes in the data point, because it just fit in the set of data point that you collect. So it does not really depend on any point whatsoever, right? So it's different, big difference from interpolation. Interpolation has to go through all the data points. For the curve fitting, it just has to fit into the set of data points that you collect. So that the differences that we had between interpolations and curve fitting. So now moving on to the following table, I just want to make a quick comparison here. So for interpolations, it's guided by the data that have been carefully collected, but of course, there's always some uh, measurement error, right? Compared to curve fitting, we just want a model or a curve that satisfactorily explains the situations under investigation. It doesn't have to go through all the data points. The second difference is that interpolations a curve that capture the trend of the data. Okay. While the curve fitting accepts some deviations, right, between the model and the collected data point. Interpolation is used to predict um, some measurement within the data point. Right? While the curve fitting strongly suspect the relationship of a particular time frame. So when you have a set of data points, you can use linear functions to fit the observations data point, or you can use quadratic function, exponential functions. Right? You can use many type of functions. Just trying to find the best fit for your data set. Okay. Now we talk very briefly mentioned about error to occur in measurements, right? But there are actually 4 different type of, or 4 basic type of errors that you see from time to time. The first one is the formulation error. The second one is the truncation error. And the third one is the route of error. And the fourth one is the measurement error. Okay, so for the formulations error, is come from assuming certain variables are negligible, right? It's always occur in math modeling because there's so many variables in a phenomena, right, in the real world situations. So sometimes you have to choose a variable such that you can just neglect it and just focus on the main variables, right? And when you neglect certain variables, of course, some error will occur, right? So that error is going to be called the formulation error. Or sometimes you make a simplifications for with the relationship between the variables. Okay. And even the best model available, there's always formulation error. Okay, now moving on to something called truncation error. It's actually coming from numerical method used to solve a mathematical problem. And it's occur in computers and calculators all the time, right? So the computer that you use, the phone that you use, always have truncation error, right? Because they cannot carry infinitely many terms or infinitely many calculations. So they have to truncate or cut up a certain part of the calculation or certain part of the formulations. All right. So for example, in calculus 2, you learn about Taylor series expansions or Maclaurin series expansions. And the Maclaurin series expansions for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. And as the matter of fact, this is the summations for n going from 0 to infinity of x to the power n divided by n factorial. So that's the series that we learn in calculus 2. Right? However, this happened a lot in practice and especially in numerical method. You don't carry infinitely many terms. However, you cut up certain part of the term so that it still not only present the value of the functions that you want to find, but also you don't produce a big error in your calculations. Right? So for example, you after x squared, you truncate the rest of the series, right? And then just focus on and just focus on the first three terms. And as the matter of fact, usually in numerical method, they use this notation, a big O notations, to indicate that, okay, after x squared or at x3 and so on, we don't care about that. It's not significant to include the term after x squared in the calculations. The third error is called the round-off error, right? It's actually coming from using a finite digit machine for computations. So for example, you have 1/3, right? So we'll give you a rational number, and it's represented by the number, decimal number 0.323, right? So on and so forth in 8-digit arithmetic. Right. Now, if you use your phone to do some calculations, you put 1/3, they might give you a decimal number with certain digits, right? Use a computer, or you use a calculator, it's always give you a decimal point with certain digit of arithmetic, right? And when you take this number, decimal number, and you multiply back, let's say 1/3 here, it's not going to give you 1 back, right? So that's just unfortunate, right? So that is the arrival of error because you cut up certain digits in the calculations. And because there's the 8 digits here, the error is 10 to the -8. And that error occur, even though it's very small error, but it's still an error, right? It's due to the round-off. And when you do calculations in using computer, using calculator, you must always expect a round-up errors to be presented in your calculations. Okay. And the last one is called the measurement error. Right. So of course, coming from imprecisions in the data collections, we always make this type of mistake, right? Even though it looks fine using your own eyes, but actually there's always some measurement error occur in your data collections. So may include human errors in recording or reporting data or the actual physical limitations of the lab equipment. Not only we make certain errors, but also the equipment that we use in the lab or the computer that we are using. It's always another set of errors that get introduced into your measurement. Okay, so be aware of that. So that's it for us for this lecture. Please let me know if you have any questions. Thank you.